So to run the main SimDist analysis for ASTM D7169, we're going to run a carbon deciphered solvent blank. Crude oil is just a bit too much for to inject neat, so we're going to dilute it down in carbon disulfide. It's about 1%. So we're going to run a carbon solving blank. We're also going to need to calibrate the GC. So what we're going to do is we're going to run a calibration mixture, which is a number of straight chain alkanes from C5 up to C100. And we know they're well tabulated is the boiling points of these straight chain paraffins, alkanes. And from the retention time that comes out in the GC, we were able to plot, map the boiling point. Chromatography wise, it's not a case of we want to separate all the peaks. It'd be very difficult for us to do that on the GC, and it's not really required. What we want to do is map the boiling points of the cuts, of the fractions using GC. So we're going to run this alkane mixture, and that will allow us to calibrate retention time against boiling point for our sample. Now, not all the sample may elute off the column. Some of them will not, all the crude oils may not elute. So we'll run a FFID detector response sample, and that will allow us to get an idea of the recovery of the sample from the GC. We can also run a validation standard. This is very useful. It allows us to validate the software and the hardware and making sure that we're getting good recoveries, we're getting good consensus values, and it gives us confidence that the instrument is actually performing. And then we can go and run our crude oil samples that have been diluted down into carbon disulfide for the GC analysis. So here's our chromatogram for the solvent blank, the carbon disulfide blank. So I think it's a bit overscale, it's gone overscale for the carbon disulfide solvent at the front, at the very beginning of the chromatogram. And then we have the background signal. This is important, just as important having the solvent at the beginning, is we want to have a good repeatable solvent blank while running this instrument. And we want to have a good bleed profile that's consistent. We want consistency with the blank because we're going to subtract the blank. The blank is important because we're also adding carbon disulfide to the crude oil sample to enable it to be injected into the GC. So if we have a consistent blank, our subtraction signal that will be quite accurate and reproducible for our crude oil samples themselves. So the blank is important for that matter, and it's not just the solvent peak we're interested in, but also the elution of the column bleed at the end as well. We want that to be nice and repeatable. So there's a typical blank from the carbon disulfide solvent. Next, now this is the retention time standard against boiling point calibration. So we've got a wax sample that's been added with some straight chain alkanes, and that allows us, in this example, we have run from C8, the first peak, all the way to the last peak, which is 49 on the list. The table will be a bit small on your screens, but at the bottom is peak at 100, which equates to a boiling point of 720. So these boiling points are in the databases, and they're well documented in literature. And we use them, what we're going to use them to do is to calibrate the software. We will then input the software, the retention times. We tell the software the retention times of each of these individual peaks. We mark out and tell the software where C8, C9, and C10 are eluted. And then that will allow it to build up a calibration curve that will then allow us to map across the retention time to a boiling point. So here is our calibration curve that we're going to use. This is allow us to map the retention time inside a GC to boiling point. So you can see we go all the way up to 700 degrees Celsius. Its retention time is in about the 30 minutes mark. So it's retention time versus boiling point. So this is the important calibration standard And this allows us to map the boiling point of the crude oil and get our TB total boiling point curves. Next, we'll run an FFID detector response signal. This is really just in cases where the sample will not fully elute from the column, is that we'll be able to monitor the recovery, see what the recovery of the sample would have been. Now for this, we're going to use the reference oil 5010 as the response factor for the FID. So that's important to be running this ASTM, maybe a bit different from your other SimDist analysis, but it's included in the 7169 ASTM. Because also we'll use the same oil and not only to get the FID response, but also we'll use it to validate our analysis, both the hardware and the software. So these in the table here, on the right-hand side, we've got a column for the cut point, the initial boiling point to the final boiling point in 10 degrees. And then we have a consensus value for the cut point. So the initial boiling point has a consensus value from the ASTM standard of 428 degrees Celsius. Our GC analysis calculated the result of the initial boiling point of 426.3 degrees Celsius. And we're allowed the allowable difference of 9 degrees Celsius, so we're well within the allowable difference for the consensus value. And here we have the cut point all the way up, and we are in well agreement with the allowable difference for the cut point up into the final boiling point of 655 degrees Celsius. And we have, on this GC result, we have 648.7. So it gives us good confidence by running these validations, these certified reference materials, that the GCs, when they leave the factory and when you use them, is fit for purpose and is accurate. So now that we've set up the GC, we've run our blank, because we're going to do a subtraction of the blank. We have run our straight chain in alkane mixture all the way up to C100 to map the boiling points. We've got a response for the FID. We've validated the analysis. We're ready to run our samples. So here's an example of a crude oil sample. It's a lot of light 10s on it, this crude oil sample. So there we have an example. We're not, I mean, what I should emphasize here, we're not, it's not important for us to have complete resolution of the individual peaks of the crude oil. That'd be very, very difficult for us to do. What we're going to do is we're going to take that retention time versus boiling point curve, and we're going to map across the results to produce that distribution curve for the boiling point of the crude oil.